Dear ladies and gentlemen, in my presentation I want to show you how you can obtain both high resolution and high depth of field by using blue LED light for machine vision. I am Dr. Claudia Link. I am the head of the Department of Optics Development here at Vision and Control. Vision and Control has more than 30 years of experience in the field of machine vision. It is located in Suhl, Thuringia in Germany. We offer a coordinated modular system of optics, vision systems and lightings. We have a worldwide network of partners for integration for our components, and with our experience we can offer for these components highest quality, reliability and precision. At Vision and Control we have an in-house series of telecentric lenses. They are developed, manufactured and tested in our company. Here is the outline of my presentation. At first I want to show you some special features of the Blue Vision telecentric lenses. Then I want to show what are the characteristics of the spectra of state-of-the-art LEDs. Then I want to show something about the sensor properties. Then I want to show what are the challenges in the optical design for blue LED light, a special telecentric lenses. Then I want to show you how you can evaluate your lenses by showing different evaluation criteria. Then I want to show you the relation between resolution and depth of field. Then I will present some application examples, and finally I will give you a summary and an outlook of future developments. So what are the special features of our Blue Vision telecentric lenses? In general, you can say you get half the wavelengths compared to previous applications, and thus you get double resolution or double depth of field. We have a stepped diameter of the object for our telecentric lenses from 18 to 125 millimeters. This means we have 6 series. And these telecentric lenses have a special color correction for the blue LED light, and with this they are predestined for use with white LED light from 440 to 660 nanometers. So what are the characteristics of the spectra of the state-of-the-art LEDs? Here I have shown you two graphs of measured spectra of two LED types. This means of a blue light LED and a white light LED. And we see the blue light LED has a peak at a wavelength of about 450 nanometers with a full width of half maximum of about 18 nanometers. And we see that the white light LED has nearly the peak at in the blue as the blue light LED. This means at 440 nanometers, and this peak has also a full width of half maximum of 18 nanometers. But it has a second peak at about 450 nanometers. This means in the green light, and this has a very broad full width at half maximum of over 120 nanometers. And here we see that the spectra of both LEDs are quite similarly, and that the white LED has a very strong portion in the blue. So in summary, for modern LEDs we have a full width of half maximum of the peak wavelength of 20 to 30 nanometers, and we have also a full width at 20% of the intensity of 40 to 60 nanometers. And this means it has a certain width of the spectral distribution, which we have to take into account when making an optical design of this telecentric lenses. And the white LED has a peak very similar to the blue LED, and it has a secondary peak at 450 nanometers. In the following table, I have listed the radiant efficiency of the LED, which we have measured, and the quantum efficiency of the sensor we have used for our tests. And then I have calculated a total efficiency. And here we see, if we only look at the LED, we see here that the blue LED is the most efficient with a radiant efficiency of 52% of the LED. And for modern developments, I have read values up to 70%. And as a next we have white LED. It is also very efficient with here 47%. Then it is followed by red, infrared, and less efficient is the green LED. And we have also here the quantum efficiency of the sensor, which is quite similar in the visual spectral range, and it is only has a decrease in the infrared. So it is quite comparable. And with this both together, we see that the total efficiency at the blue spectral range is the most efficient, with here 31%, followed by white light, and then corresponding to the efficiency of the LED by red light and green light. And less efficient is the infrared LED in this case. Okay, in the next section, I will concentrate only on the sensor properties. We have here the quantum efficiency, which was measured by our partner Allied Vision Technologies. And here you see that it is quite flat in the visual spectral range. This means from 450 to 650 nanometers wavelength. And you see then a decrease in the infrared light. And here I have combined the quantum efficiency curve of the sensor, normalized, with some spectra of modern LEDs, and also of the V lambda curve of the human eye. And here we see an opposite of the V lambda curve of the human eye, which is most efficient in the green, that the sensor curve is quite flat, as I said already. And this is why the high efficiency of the blue or the white LED can be used by the sensor, and there is not a strong loss caused by the sensor. In the next part, I will show you some of the challenges in the optical design for blue vision lenses. Here we have a typical telecentric setup. We have here the object plane, and here the image plane, and here we have the lens. And for telecentric setup, it is necessary that the aperture stop is situated in the focus of the front lens. And for correcting this system, we have to take into account, of course, coma, or we have to correct for coma, astigmatism and field curvature. Then we have to correct for distortion. This should be kept to a moderate amount. And you can often correct for distortion by using a calibration curve. But we have found out, because of the large dispersion in the blue spectral range, we have to take into account axial color and lateral color as well. Here I have shown you the dispersion curves of two typical optical glasses, and you see that the index of refraction increases as the wavelength decreases, and the increase is more or getting steeper the lower the wavelength gets. Here at this part of the graph. In the next part I will show you some evaluation criteria you can use in machine vision. So first we have the resolution. We can use, for example, for evaluating the grating period of a grating which is imaged by the lens. It has ideally an sinusoidal intensity distribution, and you see here at a low f number or a large diameter of the aperture stop, we have an higher contrast on imaging of this grating period compared to a large f number or a low diameter of the aperture stop. And here you see that the contrast of the same grating period is reduced. Here you see the boundary contrast of nearly 20% or 0.2. The maximum transmissible spatial frequency is called R max dash. Dash is always used for image sizes. And this is the inverse of this grating period. And here I have a summarize for the resolution. So I have already said that the period of a grating that only provides a contrast in the image of 20% is used as a maximum resolution. The smaller this period is, the higher is the resolution. But this period is the inverse of the transmitted spatial frequency, and the higher this frequency is, the higher is the resolution. And as I showed already, the maximum transmissible spatial frequency is called R max dash. And here I have a relation for this maximum frequency. You can calculate it by using the following formula. It is inversely proportional to the f number n and the wavelength lambda. Here we have the same slide again, but I have here also an example for the spatial frequency. Here we have 50 line pulse per millimeter at this point, and this is a grating period of 20 microns, which is quite typical for imaging in machine vision. And you see that you have here a high modulation transfer function, or which is quite the same as a contrast. And if you have a large diameter of the aperture stop or a small f number, and at a large f number you have a low contrast or a low modulation transfer function. Another typical criterion for evaluating images in machine vision is the edge steepness. For explaining this criterion, I have given you the following figures. Here I have the calculated edge spread function for a typical setup for an F number of 6 and an F number of 25. Here at the low F number we have the width of the intensity level from 10 to 90% of nearly 5 microns, and this is much smaller than we have at a large F number where it is nearly 20 microns. So here we have the definition. This means the edge steepness is defined as the edge width in the image space between the intensity levels of 10 to 90%. And of course, the smaller this value is, the greater is the edge steepness, and the better is the image quality. Here I have shown you the figures again, so we can see here we have a sharper image at the small F number compared to an unsharper image at a large F number, and this holds for the same wavelength. And the next I will show you the relation between resolution, edge steepness and depth of field. For this I have taken some calculations with a standard optical design software. I have obtained this table, and I have done these calculations for an image scale of 0.5. I will come back to this table later. Before I want to show you some correlations which hold in general for the depth of field. For the depth of field we have the following formula. This means it is directly dependent on the permissible scattering circle diameter in the image. This can be, for example, the size of the pixel. Then we have a direct dependency on the F number, and we have an inversely dependency on the square of the image scale. We see here that there is not the wavelength in this formula. This means that it's not dependent on the wavelength. The depth of field is in general not dependent on the wavelength. From this I can conclude the following for the depth of field. The ratio between two F numbers, one step apart in the F number scale, is 1.4. And this corresponds doubling or halving the amount of light. But this is also the ratio between the wavelengths for the red and the blue, which is also nearly 1.4. The ratio between two F numbers that are two steps apart in the F number scale is 2. However, this is also approximately the ratio between the infrared and the blue wavelength, which is nearly 1.8. So we can conclude that we can gain one F number when using blue light compared to red light for the depth of field, or we can gain two F numbers when using blue light compared to infrared light. And this relation is independent on the image scale. I come back to my calculation table where I want to highlight the following details. So I have here different F numbers, and I have here different wavelengths in the visual spectral range and in the infrared. And we have here F number 6, and I have a resolution at blue light for example from 8.2 microns, and a depth of field at blue light of 2.5 millimeters. And if I go to infrared light, we see here that the resolution is decreased. This means the edge creating period is larger, which is here 15 microns nearly, and the depth of field is the same as in the blue. It is nearly 2.5. We have it here. If we now go to F number 11, we see that the resolution is compared to F number 6 nearly halved. This means it is 15 microns, and the depth of field is nearly 5 millimeters, or which is nearly the double. And we see the resolution at F number 11, which is 2 steps in the F number scale, is the same as in the infrared, as I use F number 6, but I have double the depth of field. Now I want to show you some applications. At first, I want to show you the advantage by using blue lights in the resolution. Here we have the same setup, one times imaged with blue light and one times imaged with infrared light. And we see here that we can still resolve at the USAF chart group number 8, element number 9, with a grating period of 3.91 microns and a spatial frequency of 256 line pulse per millimeters, whereas we look at the infrared image, we can't resolve this anymore. Here we have an example for a high depth of field by using blue light. I have used for imaging this dot target the lens TO18/9.0 for imaging a field of 18 millimeters to sensor diagonal of 9 millimeters, and the grating period was 1 millimeter, and it was imaged in transmission. And we see here at Z equals 0, the object is placed in the ideal object plane, and here it is set in the far depth of field plane, and here in the near depth of field plane. And at F number 22 we have a sharp image within a depth of field of nearly 5 millimeters. Here's another example for a high depth of field. I have here the settings F number 16, blue light at 470 nanometers. I have here a telecentric lens TO18 / I have here the telecentric lens TO18/9.0 again. Here I have used it in reflection to image this mechanical component, and with a depth of field of 5 millimeter we can have this 3 circles sharp and can measure this. Here we have an example for imaging in reflection again. Here we have one time imaged the integration circuit board with blue light, and here with infrared light, and we can see here that we can read the components because they are imaged sharply from the bottom and from the top of this integrated circuit board, where we have here the case that the components are sharply imaged on the top of the integrated circuit board, whereas they are unsharp on the bottom. Now I want to summarize my presentation and give an outlook to our planned and developed lenses. I have shown you that in the interplay between the LED and sensor efficiency, we can see that the most efficient is the blue LED. In general, we can say that compared to previous applications with red or infrared light, we get nearly double the resolution or double the depth of field. Now we can use the high potential resolution or the high depth of field when using imaging with blue light with the new developed telecentric lenses. And because I have shown you that the spectrum of the blue LED and the white LED are quite similarly, the telecentric lenses also work very well with white light. Our lenses are stepped by the maximum imaged object diameter, and this is also the name of the series. This means the TO18 series is used for imaging a maximum object diameter of 18 millimeters, and so the TO30 series for maximum diameter of 30 millimeters, and the TO44 series for maximum diameter of 44 millimeters. They all have a standard C-mount adapter. They are developed for typical sensor sizes. This means for 1/4 inch with a sensor diagonal from or of 4 millimeters to 2/3 inch with a sensor diagonal of 11 millimeters up to 1.2 inch with a sensor diagonal of 21.4 millimeters. And we have also one lens in each series which is optimized for the so-called DX format with a sensor diagonal of nearly 28.5 millimeters, and this needs a special mount. We have here an M42 mount. Then we have a series for a maximum object diameter of 66 millimeters, the TO66 series, which goes for sensor sizes from 1/3 inch with a diagonal of 6 millimeters to the maximum diagonal of 28.5 millimeters at the so-called DX format, also with C-mount and M42 mount adapter. For larger diameters we have the TO88 series and the TO125 series, which are also developed for typical sensor sizes from 1/3 inch to DX format. They have also the C-mount or correspondingly an M42 mount. Now at the end of my presentation you can contact us by my email address, and you can also visit our website where you can see the latest developments and you can get some information about our telecentric lenses. I want to thank you for your attention.